Hello everyone, my name is Dr. K.C.H. Apparao, working as an associate professor in mechanical engineering department. Okay, in last class we discussed the question bank discussions, mainly the concept of loss of radiation. So in this class we'll see the importance shape factor or view factor or and next to radiosity. What is the radiosity? Next we'll derive that equation, derivation of heat transfer in a single plate. So through radiosity. Okay, you will see what is shape factor. It is also known as the shape factor or angle factor or geometric factor also or configuration factor. Okay. So what is the importance of that one? We will see. So it is purely a function geometry of two surfaces, just positioning or geometry of two surfaces, orientation of one surface with respect to other. Okay. The space between the radiating surfaces. So the space and orientation of one surface with respect to other. These two, based upon these two, will take the view factor. So it is independent of system's surface properties. It is not dependent upon the properties of temperatures. It is positioning or orientation of one surface with respect to other. Okay. The view factor of surface I with respect to j. So it is denoted by Fij with respect to I. So view factor of surface I with respect to j. Okay. So Fij shows view factor of I with respect to j. Okay. It is defined as the ratio of the radiation energy leaving a surface I and that reaches the surface directly to the total energy leaving that surface I. Okay. So view factor. So radiation energy leaving surface I and that reaches the surface directly or total energy leaving the surface I. Okay. So therefore the view factor F12 represents the fraction of radiation energy leaving surface 1 and that reaches the surface 2. Okay. Similarly, F21 energy leaving surface 2 and reaches the surface 1. Okay. So Fij energy leaving the surface I and reaches to j. So Fi2I energy leaving surface I and leaving the same surface. The fraction of radiation energy leaving surface I that strikes itself directly. Okay. So you can understand this one view factor by this just to denotion. Okay. Some evident results you can see for flat and convex surfaces. The view factors F11, F121. So same surface leaving to and reaches the same surface. So for case of flat and convex, okay. So convex surfaces for the flat surfaces. So F11 is always 0. F11 is always 0. It means energy once leaving the surface never returns to that surface. If the surface leaves from here, it never comes to same surface here also. The energy leaving from this surface never touches this one. But in case of this, so it means for the flat and convex surfaces, you can take F11 is equal to Fi2I is equal to 0. Okay. We'll see this one. This is the flat surface, plane surface. F11 is equal to 0. Fii, so same surface leaving and same surface reaching 0. For convex surface also, the energy leaving from this surface never touches this surface again. Okay. So F11 is equal to 0. Fi2I is 0. But in case of concave surfaces, some energy may reaches the same surface again. So here F11 not equal to 0. So from the concave surfaces, the shape factor with respect to itself is never 0. It means radiation energy coming out, a portion of surface will be absorbed by the same portion, other portion, same surfaces. Okay, so it is F11 not equal to 0. So we will see some assumptions: uniform radiation in all the directions. The medium between the two surfaces doesn't absorb any absorb or emit or scattering. So we are not considering the medium between the two surfaces. Fi is the fraction of radiation leaving I and touches the surface J. Fij is 0, indicates two surfaces do not see each again, okay, each other. So Fij is equal to 1, indicates the surface J is completely surrounded by surfaces. So this is the one surface is covered by another surface. Then Fij, this is I, this is J. Then Fij is equal to 1. How to remember this one? So some cases here you can see these are the flat plates. F1 to 2 represent the fraction of radiation. The energy leaving the surface 1 and that is reaches the surface 2. So and F2 1 shows the energy leaving the surface 2 and reaches the 1. Okay. Then Fij, energy leaving I and reaches the J. Okay. So you can see. So this is the condition. Here these are the flat surfaces. F12 is equal to F21 is equal to 1. Okay. So here F12 and 2 is equal to 1 by 2. F12 here 1 by 2, but F2 to 1, so that is the 0. You can see here F12 is equal to just to half into F21. You can observe the some conditions. Next, there are some rules to identify the shape factor. The first one is the reciprocating rules. This is the what is shape factor? What are the types of methods to find the shape factor? So this is the question, very important, which is given in the question bank. Just I am addressing that question. Listen, okay. The first method is reciprocating rule. A reciprocating method, a reciprocating rule. According to this one, A1 F12 is equal to A2 F21. Okay. So area into energy leaving from 1 to 2. Okay. Here area 2 into energy leaving from 2 to 1. Okay. So it is, this expression is termed as the reciprocating rule. It is very useful in determining one view factor from the knowledge of the other. So with respect to one another, we can determine this one. So next one is the summation rule. What is summation rule? If an enclosure consists of n surfaces, okay, the conversion energy principle requires that the entire radiation leaves a surface I must be absorbed by all the surfaces of the enclosure. Okay. So therefore, the sum of U factors from surface I of an enclosure with respect to all the surface of the enclosure, including so itself, this must be unity. So that known as summation rules. Here you can see. So these are the summation rules. Okay. So summation rule. So surface 1, surface 2, surface 3. F11, F12, F13 is equal to 1. Summation is equal to 1. Similarly, with respect to surface 2, F21, 22, 23 is equal to 1. With respect to surface 3, okay, F31, 32, 33 is equal to 0. So this is reciprocating rule. A1 F12 is equal to A2 F21. Here only in summation rule we will see only U factor. Sum of the factors is equal to 1 with respect to surface 1, with respect to surface 2, with respect to surface 3. Okay. In reciprocating rule, we will see areas of the two surfaces also. Okay. So total number of U factors. How to find out the total number of U factors here? So this is the formula of into n minus 1. You can see. Okay. So suppose n is equal to 3 surfaces are there. Then you can use this formula. half into 3 into 2. So total 3 view factors are there. Okay. So here long surfaces, flat surfaces, two infinitely long parallel planes separated by small distances. In this case, F11 is equal to 0. The energy leaving the surface doesn't meet the again. Here also energy leaving the surface doesn't meet the again. So F11 is equal to 0, F22 is equal to 0. Okay. So summation rule here, the two surfaces are there. According to summation rule, F11 plus F12 is equal to 1. If this is the 0 means automatically F12 is equal to 1. Okay. So similarly, F21 plus F22 is equal to 0. So F22 is equal to 0, we know this one. Then automatically F21 is equal to 1. So we can remember this one, F12 and F21 of any infinite parallel plates. Okay. So these are the enclosure conditions. Okay. So body 1 is enclosed by body 2. So here we can use the reciprocating rule. Area of first body, that is the first surface, A1 is equal to 2 pi R1L. What is the, suppose cylinders, one cylinder is enclosed by another cylinder. So area of the first cylinder, area of the second cylinder. Here F11 is equal to 0 because this is the concave convex condition F11. Then so according to that summation rule, F11 plus F12 is equal to 1 means F11 0 means automatically F12 is equal to 1. Okay. So similarly next to A1 F12 is equal to A2 F21. Then you can substitute the A1 and A2 areas. Then automatically F21 you can find out. F21 is equal to R1 by R2. So for solving the numericals, these view factors are very important. Then you have to understand how to find the view factors and how to write the view factor in solving the numericals. Okay. Next one you will see radiosity is the very important term. So by using the radiosity, you can find out the radiation heat transfer rate in the particular surface. What is the derivation? What is the rate of heat transfer formula in particular surfaces by using the radiosity and irradiation G. Okay. So radiation is the number of photons that are being emitted by a single surface. Okay. You know that radiation, number of photons. So thermal energy transfer in the form of the photons. So number of photons that are being emitted by a single surface. We are considering only single surface. Okay. So irradiation is nothing but where the radiation is falling on the surfaces. Suppose this is falling on the surfaces. This is represented by G. When the radiation energy is falling on the surface, it may be absorbed, it may be reflected, it may be transmitted. Okay. So this reflecting, you will see that reflecting and some energy emitted also. Reflecting, that is a rosy, but emitting energy, EB. So this is nothing but radiosity. So that is represented by J. Radiosity is the radiant heat flux, radiant flux leaving, emitted and reflected and transmitted. For if you consider this is opaque bodies, the transmission is 0. Okay. So then emitting energy and reflected energy. This is reflected and this is the emitting energy. So the addition of both, that is called radiosity. Here we'll see. This is the incident radiation for the opaque surfaces. Some portion will be absorbed. So because of that one, some energy will be emitted also. So this one is the reflecting energy, rho G, plus this one is the emitting energy, epsilon into EB. Okay. So the addition of this one, it is called J, radiosity. Okay. So opaque surface, you know that there is no transmissivity. Alpha plus rho is equal to 1. Okay, if you know the Kirchhoff law is nothing but alpha is equal to emissivity. Then emissivity plus rho is equal to 1. Then rho is equal to 1 minus emissivity. Okay, you can write like this one also. So Q is equal to rate of heat transfer. So in this particular surface, rate of heat transfer in this particular surface, that Q is equal to radiosity minus incident to radiation. So this is just we have to derive this one, radiation rate of heat transfer in a particular surface by using this radiosity and incident radiation. Okay, so we'll see. So J is equal to, you know that J is equal to rho Z plus epsilon EB. Okay, so this is the reflecting energy, this is emitting energy. Then we know that according to Kirchhoff law, J is equal to rho is nothing but 1 minus epsilon G plus epsilon EB. Okay, so this one, then you can rewrite like this one, J minus epsilon EB. Just turn this, send this term to left hand side. Then J minus epsilon EB is equal to 1 minus epsilon into G. Then automatically G is equal to J minus epsilon EB by 1 minus epsilon. Okay, so then this is the G value. We know that the J value also. Then you have to find out the rate of heat transfer Q. So we'll see how to find out the rate of heat transfer. So that is very important. We'll see. So in a question bank, this type of question has been given. So what is radiation energy? How to find out the heat transfer rate in a single plate? Derive the rate of heat transfer in a single plate. Okay. So okay, you know that Q is equal to J minus G value. So G is this value, you can substitute this one. This is epsilon, this is epsilon. Okay, so J minus epsilon EB by 1 minus epsilon. Okay, so next, if you, so you can take the LCM and you can cross multiply this one, then automatically you will get to this equation. So J minus J into epsilon minus J into epsilon EB. Okay, 1 minus epsilon. Then the formula will be like this one, epsilon of EB minus J by 1 minus epsilon. Okay, you can rewrite like this one, Q is equal to EB minus J by 1 minus epsilon by epsilon. So this shows the thermal resistivity. So this one is the just potential difference or thermal difference, thermal energy differences of any particular surfaces. It means emitting energy or emissive energy minus radiosity by thermal resistance of particular surface. So the radiation heat transfer in a particular surface, the Q is nothing but emitting energy EB minus radiosity by thermal resistance. Every surface has particular resistance. This is called 1 minus epsilon by epsilon. Epsilon is the emissivity, you know this one. Then the formula is equal to this one, EB, emissive energy, total emissive energy minus radiosity by 1 minus epsilon by epsilon. Okay, so this is the thermal resistance. So if you write the electrical analog formula, you can see this is the EB, thermal resistance, and the J. Okay, so this is the thermal resistance 1 minus epsilon by epsilon. Okay, you can see this one. So this resistance is nothing but surface resistance. What is this one? 1 minus epsilon by epsilon is the surface resistance. This formula is very important. This is the EB, this one is the J, 1 minus epsilon by epsilon. Okay, so radiation heat transfer rate in a particular surface means we can derive like this one. Okay, so this one is it was compared with the electrical powers. You can take this one. Okay, we will see one numerical which is based on this formula. A diffuse opaque surface. So alpha observed is given, so 0.8, and the temperature T is equal to 100 degrees Celsius. Received an irradiation means G as given, so that is the 1000 watt per meter square. The surface area also given, E is equal to 0.1. Calculate radiosity. You have to find out the radiosity. Net radiative transfer rate, it means heat transfer rate Q, you have to find out. Calculate above quantities if the surface is black. So the surface is black means MCVT is equal to 1. MCVT epsilon is equal to 1, the condition. Okay. So these are the given. Alpha is equal to 0.8. TS, surface temperature, is equal to 100 degrees Celsius. G is equal to 1000 watt per meter square. Area is equal to 0.1. Okay. So we can solve this one. First of all, we will solve the radiosity. Radiosity G is nothing but epsilon into EB, emitting energy, plus reflecting energy. Okay. You know that this is the 0.8 into EB. You have to find out this one. According to Stephen Boltzmann constant, EB is equal to sigma T to the power of 4. Okay. T to the power of 4. By using that formula, you can find out the EB. Okay. So first one, this is the opaque surface. Transmissivity is equal to 0. Alpha plus rho is equal to 1. Then rho is equal to 1 minus alpha, means rho value is equal to 0.2. Okay. Then radiosity, alpha, because emissivity is nothing but alpha, according to Kirchhoff law. You can take alpha. Alpha sigma T to the power of 4. So this is the AB formula, according to Stephen Boltzmann constant, into rho into G. Rho value is equal to 0.2. If you substitute all the values, you will get the J, radiosity value. So heat transfer rate. So heat transfer rate, you already derived the formula. Q is equal to area into PB minus J. Okay. EB minus J by 1 minus epsilon by epsilon, or 1 minus alpha by alpha. You can take. Okay. So this is 1 minus alpha is nothing but rho, reflectivity, that is 0.2. So 0.2 by 0.8. Area is equal to 0.1. And EB is the sigma T to the power of 4. Sigma is the 5.67 into 10 to the power of minus 8. Temperature in kelvins, 100 plus 273, 373 to the power of 4 minus J. So radiosity value, what was already solved, determined. Okay. So this is the value, 7.81 watts per meter square. So that is the rate of heat transfer in a particular surface. Okay. So third one, if the surface is black surface means alpha emissivity is equal to alpha is equal to 1. Okay. Then radiosity G is equal to, because radiosity is nothing but rho is equal to 0, because emissivity is equal to 1. Okay. So automatically then radiosity is equal to radiosity J in the black, for the black surfaces, EB into alpha or emissivity. Okay, emissivity is equal to 1. It means EB. So J is equal to EB. EB is nothing but sigma T to the power of 4. So then you can find out this one. So this is the J1. If you know that J1, then you can find out the Q value. So Q value formula, you know this one. Okay. If you substitute the values in that one, you can find out the Q value also. So this one is the numerical. These are the textbooks for the reference I have given. You can refer these textbooks for solving more problems and to understand the derivation of rate of heat transfer by radiation for a particular surface. Thank you for listening to this class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.